So just a couple reminders of what's happening. So the final exam will be posted tomorrow. By noon. So it's due Friday, 11:59 p.m. So also, we will have class Thursday. If for any other reason, so that you can ask questions you might have about the exam. So with that being said, two things. If this is a logistic issue for you, I know a few of you have reached out already. So if this time frame is not ideal for you, you just need to let me know and we can make other arrangements. I'm trying to be as, I don't know what the correct word is, but I'm trying to make sure that you all have an ample opportunity to do well on this. And also, I highly encourage that you look at the comments from the first two exams. Make sure, look, one of the important things is not just that you can do the math, but it's that you can communicate it properly. Look, when you leave school and go out in the real world, it's great if you can do science and math, but if you can't communicate it both on paper and verbally, then I mean, what good are you in the sense of being employable? You have to be able to communicate these things. So I can't emphasize this enough. When you're writing up solutions, it should be clear, it should be concise. It shouldn't be difficult for the reader to figure out what your reasoning is. And I really hope that you spend some time thinking about that. And if you have questions, you got to ask. So with that being said, does anybody have any homework questions or any questions at all regarding the exam or the course, grades, all that stuff? Really? So you don't see any comments? That's interesting. I'm trying. So Heather, interesting. Because when I look at it, I see them. That's weird. Wonder why you don't see them. Is that the same for everybody? Is everybody not seeing comments? That's really weird. Very, very weird. Huh. Yeah, I'm not. And maybe that's why. And by the way, that's another great point that you brought up. For those of you who are using your phone, I don't know. The interface for Canvas on your phone is clearly not going to be the same interface that's on the computer. So, because I also noticed a few of you said you can't find the lectures anywhere. Well, when I log on to Canvas, the very first thing I see is the YouTube embed and then a link to the video lectures. So I'm not sure if you're using your phone. I'm not sure exactly. We're gonna have to figure that out. Which this is, again, you have to understand that I'm sort of, this class was never meant to be online until the very last minute. So we're trying the best we can to adapt under a short time frame. And so I'm trying to use these tools that Yeah, it's interesting. So I'm looking at it now. I don't. This is weird. I don't. Yeah. So I see what you're saying now. I don't see anything. Well, I don't even see markings on this one. Okay. What if you click on the view feedback button? Do you see a view feedback when you look at your exam? That's the only way I found comments. So when I clicked on your exam submission, Heather, there's a red link that says view feedback. And that's when I saw it. So yeah, I mean, interesting. Yeah, because a lot of those blue boxes, there's a comment. Oh, okay, Michael. See, this is interesting. All right. Well, I apologize about that. I didn't realize you weren't seeing it. This explains some things. I'm going to look into that, and I will try to fix it as soon as possible. If it would be helpful, I said this before too, and it's worth noting. You guys are more than welcome to, reach out to me about discussing your work one-on-one. I mean, that's up to you, but I am available for that. I know sometimes you hear me say that, but it, if you want to go over things in detail, I'd be happy to do it as best we can through this virtual sort of world. So I'll figure that out after class, why you're not seeing them. Maybe there's a setting that I could change to make it happen right away. But, yeah, interesting. Let's see something. Yeah, of course, this is something else. I don't know. I'm gonna have to look into it. I apologize about that. So what I would ask, if you guys can, if you are seeing comments, let me know, and if you're not, let me know, so we can figure out how to make this a better experience for you guys. I didn't realize you guys weren't seeing the comments because no one was complaining about it. So, and we'll have to figure that out ASAP. All right. Does anybody else have a question about their exam or their score or anything like that? I sure can. Becca, hold on. So homework 9, question 8. All right, so this is a pretty good question. Look, one of the doing calculations is one thing, and it's important that you're able to do calculations. But as you guys know, as most of you know, and in fact all of you know, I mean, machines can do calculations for you now. They can do calculations more accurate than you and more efficiently than you. And so what you really want to concentrate on is being able to apply your knowledge of mathematics. And these types of questions, particularly on this homework 9, are what we mean by applications. How can you take your knowledge of calculus and use it to answer questions? And so, as I said when I posted this homework, I said homework 9 is long and it's difficult. And the reason it's difficult is because most of the problems aren't asking you to be some sort of robotic computation thing. What they're asking you to do is take English translate it into mathematics, and then use your mathematical skills to solve a problem. And that is a very difficult thing to do, particularly when you have very limited experience. And anybody sitting in a calculus course has limited experience. So let's look at this problem. And one thing I will tell you is that most of these questions, particularly 3, 4, 5, 6, 7, and 8, are very much identical at their core. You need to determine a function, and that function that you're determining has to be telling you, or excuse me, not telling you, but it has to be quantifying what you're interested in learning. For example, we did an example like 3 and 4. And so in number 3, we want you to figure out the minimal perimeter. And so that means if you want the minimum perimeter, your job is to determine a function that gives the perimeter. In problem 4, you want to investigate area. So you need to figure out a function that gives the area in that context. Same with problem 5. Problem 6, the same thing. Problem 7, you need to figure out a function that gives you the cost of laying cable under the conditions that are stipulated in the problem. Number 8, what we're trying to do is we're trying to determine the shortest distance between a point and another point. So what that means is the following. So the function of use is the distance between 2 points. And you'll recall that the distance between 2 points is x minus some x1 squared plus y minus some y1 squared, all square rooted. So you can think of this, some of you may have learned this as the distance formula. Others may just realize this as the Pythagorean theorem, sort of written differently. And if I draw a picture of what it represents, it just represents the following. If I have some point, which I'll call x1, comma y1, and then I have some other point, which I'll just call x, comma y, then the distance between these 2 points is d. That distance is d. Now, why is it d? Well, again, it's really just the Pythagorean theorem. But if you were so inclined, what you could do is you can just take and make a triangle out of this. And then by the Pythagorean theorem, the length of the hypotenuse is that letter d, which is given by that scary looking thing in the square roots. Okay, now the formula that I've written down, that works for any 2 points, x1, y1, and xy. But we're not interested in any 2 points. We're interested in a specific scenario. We are interested in a point, finding a point on a curve that is closest to another point. So let's go to the next page and let's sort of draw what we have here. So if we draw our parabola, the parabola is 1 minus 1/2 x squared. So you could go to a graphing device, that's fine, And when you plug in the point 0, it spits out 1. And when you plug in the square root of 2, it's 0. And when you plug in negative square root of 2, it's 0. So the parabola looks like this. Oops. Let me try that again. It's really hard to draw on this thing. Of course, you could go to Desmos or something to draw it. And then maybe what I'll do is I'll move this over here so it's a little more clear. And then what we're interested in is we're interested in how this curve is geometrically related to some other point, which I'm going to draw in red, which is up here. All right. So that should be actually 1/4, not 1/9. And so what we're looking for is we're looking for the magical point that's on this blue curve. Our intuition tells us it's not over here and it's not over here, but we're looking for the point on the blue curve where this distance is shortest. So let's label this point XY. So we need to determine X and Y that makes D as small as possible. So does anybody have a question so far about how I'm setting this up or how I'm thinking about it? Now's the time to ask if you do. Now, let me reiterate this because often you guys get worked up, not worked up, that's a bad way of saying it, but maybe overwhelmed. This is not, look, if you're in a calculus course and either A, you don't know how to graph this guy quickly, or B, don't know how to go to a computer or a calculator to get the graph, then you need to reevaluate how you're studying calculus. Because at this point in the game, if you're wasting too much time just sketching the graph of a simple parabola, then you're not preparing properly. And I'm not saying that to be mean or disrespectful. I'm saying you need to think about how you're preparing this stuff. Look, the higher up you go in these classes, the more and more is assumed of you. I mean, most of you first learned how to sketch parabolas, these second order equations, probably in 8th or 9th grade. I don't know, whenever you learn algebra now, maybe 10th grade, I don't know. And so at some point, these are things that need to become natural. Just like if you want to play baseball, guess what? At some point, if you can't catch the ball and you can't throw the ball and you can't run, you don't get to play baseball anymore. And so, I'm not trying to be negative. I'm not trying to defeat, bring you down or make you seem like and I don't mean to say that you're stupid or not smart enough. I shouldn't say stupid. That's bad. But what I'm trying to tell you is, it's hard to learn calculus when you haven't mastered the prerequisite things. And so, again, if you don't know how to draw this picture without help, that's fine, but you should at least know how to draw this picture on Desmos or on a calculator. And so I can't emphasize enough, if that's something that you're struggling with, you need to reach out to me. You need to go to the tutors. And it's not just for this class, because many of you will have to take more math. And guess what? In Calc 2, everything you learned in Calc 1 is going to be assumed that you know. and it really builds fast. And then many of you are going to have to take physics classes, and everything you learn in calculus, it's going to be assumed that you know in physics. And so again, I'm not saying this to beat people down. I'm saying this because I want you to understand the situation. So the last thing I'll say about this is make sure that things like this, knowing how to draw an elementary curve, are things that you can either do in your head quickly or you can easily get from technology. So please keep that in mind when you're preparing. It's going to be for your benefit. All right. So let's go back to the problem. Hold on one second. I got very thirsty. Okay, so cool. So just like in the examples we did last week, we need to get a function. And what we've written on the previous page is technically not a function in the sense that we're used to yet. We have to make it a function because that we can use, because right now this function has lots of variables but no numbers. So if we note that this guy is if we apply it to this particular situation, we have x minus 1 comma square, or excuse me, quantity squared plus y minus 4 quantity squared. And even at this point, this equation is useful, but it's still got one too many letters for us. And what we can do is we can eliminate one by using a constraint. We are not interested in any x or y. We are interested in a point specifically on that curve. And so that means its x and y coordinates have to satisfy the following. So we can replace y with what it must be equal to if it's going to be a point on our given curve. And so if you clean this up, the function you really want to worry about is this. So this becomes -3 minus 1/2 x. Well, there's a square in here, and then this is all square. Excuse me. So if you get this far, you're far, and that's good, but there's still a lot of work to be done. Does anybody have a question at this point? Okay, so the good news is we now have a function of one variable. So everything we know about functions of one variable, in particular calculus, that we now know that we can determine a maximum and a minimum of this creature. Of course, thinking of the actual construction of the problem, we know there's no maximum here because we can always go further and further away. But we do look at this picture and say, okay, there's got to be a minimum. And how do we determine what the minimum is? Well, calculus tells us we have to take a derivative, find critical numbers, and then test them to see if they correspond to a min or a max. And what's unfortunate about this problem is the function looks very messy. But there are some simplifications that we can use to make life easier for us. So I'm not saying you have to do it this way, but there are some sort of ways that you can make the calculations, at least on that you're going to have to do, make them a little easier. So for one, let's rewrite it so the derivative's not as bad to compute. So what I'm going to do is I am going to rewrite this as d squared equals x minus 1 quantity squared plus, now watch what I do here. You're going to be like, how did you do that? Why did you do that? I'm going to eliminate the minuses. That is not cheating. That is using my brain. I know that if I have any negative number and I square it, it's positive. So what fact I'm using here that's going to help aid in my calculation is I'm using this fact. I know that negative a quantity squared is the same thing as a squared. So I can pull that minus sign out. And when I square minus 1, I get positive 1. So I can write it like this. This is not wrong. And now another thing I'm going to do, and you don't have to do this. You could have left the square root there. That's fine. But this is going to be a little cleaner. I'm going to use my knowledge of the derivatives and really the chain rule / implicit diff to make this calculation easier. So what I have is I have 2d dd dx becomes, now I'm going to differentiate this. This is 2 times x minus 1 plus 2 times this quantity times this derivative, which is x. So that is me using the chain rule 3 times. Once on the left, 2 times on the right. And we can clean this up on the right now. This is 2x minus 2 plus 6x plus x cubed. Which if I rewrite is x cubed plus 8x minus 2. Whew, scary. All right. Now what's next? Well, look what we did. We tried to take a little shortcut. So let's rewrite this now. Remember, I'm interested in the derivative, and I have the derivative, but I have to make sure I write this properly. So what I'm going to do is I have to note that the derivative is actually x cubed plus 8x minus 2 all over 2d, which if we put d back in there, is 2 times that square root business, which I'm not going to write because it's going to be unnecessary. Remember, I need to know when this quantity is 0. So the denominator does not come into effect at all. The only thing I really have to solve is when is the numerator 0. So we need to solve x cubed plus 8x minus 2 equals 0. Because that's the numerator. So how do we do this? So we're at a crossroads because this is bad news. This can't be solved by methods learned in algebra. What I mean by that is you can't factor. So typically when I give this problem, this is where students get to, and then this is sort of where they fall apart. Because you're going to say, well, how do I solve it then? So using a calculator, computer, Wolfram, whatever, etc., you can show the solution is x approximately 0.24809. So this is a very interesting problem. We can't find the exact value. The best we can do is approximate it. Now, I shouldn't say we can't find the exact value. Turns out you could, but no one knows the formula. There's a formula that's analogous to the quadratic formula for these cubic equations, but it's really, really ugly. If you're interested, you can go look it up, but no one would expect that you know it or expect you to use it. But if you solve this, if you went to Wolfram and solved this, they would give you the actual value and the approximate value. So a good way to think about this particular problem, and it's not all of the problems, but this one is an example of this. And here's the moral here. So using the first derivative test, and I'll let you verify this. So you should verify that for yourself. And it also should be pointed out that I would not do this on an exam. So on your exam, all problems do not require approximation by computers. So I hope that's clear. And what I'm saying is on the exam, I would never give you a problem that you can't solve the critical numbers symbolically in an exact form. Here we couldn't, so we had to approximate it. We also do that in real world all the time. We approximate. Does anybody have a question about this? Becca, does that help? So I would encourage that you, if you're confused about what I mean by exact versus approximate, you should ask. That value that we found, I mean, you could get it easily on Desmos, or you can just go to Wolfram and ask them to solve. That value is just an approximate value of a number, just like we say 3.14 is an approximation of the number pi. All right. So what I would encourage you do is you study this example. Now, there are other problems similar to this where you could use the same function and you get an exact answer. I just chose this one because you do once in a while need to see that not everything can be worked out by hand. Sort of foreshadows some things that you're going to do later on as well. Okay, so any other questions before we move on? Okay, so it's time for a new topic. And that's what we're going to do. All right, so we spent the last few classes investigating applications of the derivative. So it's time now to study a new problem that seems unrelated, but turns out to be related. And what this news topic is area and integration. So let's be very clear on what happens. So a problem as old as time. Given a region in the plane determine its size. So what do I mean by that is, I mean, if we have some, sort of nicely defined region, what is the size of this? So notice I haven't used the word area yet. Even though I wrote the letter A, because the word area actually hasn't been defined. So here's a pretty cool philosophical thing to think about. So for basic shapes, this is quote unquote easy. You have the area of a square, area of a rectangle, area of a triangle. So for example, if this is a rectangle, it is very intuitive to say, okay, the size of this thing is X times Y. And then if I were to cut this creature in half down the diagonal, it doesn't take much sort of craziness to say, okay, well then the triangle should be something like, if we call this the height and we call this the base of a triangle, then the area is 1/2 base times height. So these, humans have had a good solid understanding of this for quite some time. It seems reasonable that if we're going to assign a number to quantify the size of a shape, well, this is very natural for a rectangle. And if it's natural for a rectangle, then it's clear for a square and a triangle because we can deduce it logically. The problem is, in general, for curved regions, it's not so obvious. So that is a question that has kept some of the smartest people for thousands of years sort of in the dark. How do we properly define area so that we can quantify the size of curved regions? So how do we properly define area so that we can quantify the size of regions with curved boundaries so that this definition works for rectangles, squares, etc. So this is the problem that has given mathematicians and philosophers and scientists for quite some time, actually up until the 1600s when calculus was invented. We didn't know how to properly do this. And in many ways, we still didn't know how to properly do it into the 1900s. So a problem that's as old as time, how big is something, has taken thousands of years before we actually were able to properly answer the question. You know, you guys were often taught in school to memorize that the area of a circle is pi times its radius squared. But if I asked you where that comes from, you would have a very hard time of explaining it. Now, of course, if you understood calculus, you can better explain it. But the fact of the matter is, you need to understand calculus to explain where the formula for the area of a circle comes from. Does anybody have a question? Okay, so one way to do this is to construct the so-called the Riemann integral. Or some people call this the definite integral. So we haven't told you what that is yet. We're going to tell you. But it's nice to sort of tell you, where we're headed. So to motivate, we're going to consider an ancient problem that actually Archimedes solved many, many years ago, but we're going to solve it differently. And it's going to help us recognize that there's a bigger picture, a big theme hidden in everything. So let's motivate this way. So let's take the function f of x equals x squared. And let's just restrict ourselves to the interval 0, 1. And so let's say, what is the area, quote unquote, under the curve? So that might not be clear to you right now, so let's draw the picture. So if I draw the graph of this function, we know that it comes up like this. And of course we know that it goes like this. But what we're interested in is we are only interested in this region that I'm going to shade in pink. So what is the area of the pink region? So this is the problem we want to solve. So if we said to you, how might you do this, and we let you brainstorm for a while and get in groups, you might come up with some good ideas, and eventually you would come up with the idea that we're going to use. Because once you see it, it seems rather intuitive. And what I want to do is I want to illustrate it, but in order to not just save time, but to also help your mind see what's happening, I'm going to show you a sort of a graphic of this before we do anything else. And so what I'm going to do is the following. I'm going to turn the screen to a new share, and I'm going to take us to a website that's very similar to Desmos. It's called GeoGebra. And hopefully you guys are seeing GeoGebra right now. Yeah. And what I'm going to do is I'm going to type in the function that we're interested in. And the reason I'm going to use GeoGebra is it has some nice built-in things that that Desmos doesn't. So you don't really need to pay attention to what I'm typing right now, because you're not going to understand it, and that's okay. Give me 1 second. So what I'm going to do is I'm going to zoom in. Here's the region that I drew on our whiteboard. And this is the region, the area we want to determine. And so let's think about how we might do this. And one idea is to use rectangles to sort of approximate it. So what I'm going to do is I'm going to first say I'm going to draw 4 rectangles. And what you'll notice, and I want to change my color here. Use pink because that's what we're using. So the observation here is that if I use 4 rectangles, I get a very, very crude approximation of, and don't even think numerically, but just think of aesthetically. I have 4 pink rectangles, and they clearly don't match this blue curved region. But the idea is if instead of me using 4 rectangles, if instead of 4, maybe I say I'm going to change this to 8 rectangles. What happens if I go to 8? Well, from an aesthetic point of view, it looks like all the extra overlap has sort of disappeared, or the excess of the approximation has disappeared. And then I say, okay, well, what if I, instead of using 8 rectangles, I use, say, 20? Well, now more and more of that excess has disappeared. So I say, what if I, instead of drawing 20 rectangles, what if I spend time or use a computer to draw 40 rectangles? And so what we're seeing is, as I decide to draw more and more rectangles, the actual blue region hasn't changed, but the pink region, that is the sum of 40 rectangles, is shrinking down to match the blue region. So if me, instead of doing 40, I decide to do 80, you'll see that it becomes more and more like the blue curved region. And then if I say y80, let's double it. What if I draw 160 rectangles? And now when I draw 160 rectangles, I see that this pink region is becoming more and more to look like the blue region. Now, of course, if you zoom in, you'll realize that there's still these tiny little steps. But the point of the matter is I can continue to play this game forever and ever and ever. What if I did 220 rectangles? You're going to be hard pressed to tell anybody who just walks in and looks at your computer that that is 200 rectangles. They're going to think that that's just some pink shape. And one more to grow on. Let's just, for the heck of it, let's go up to like 500 rectangles. And again, that does not look like 500 rectangles to anybody. That looks like what? It looks like a sort of triangle with a curved hypotenuse, or it looks like the area or a region under a parabola. Does anybody have a question about this? Comments, concerns? So I think everybody, I think what you need to do is convince yourself that this is intuitively a cool idea. Just take your region that has curved sides and keep chopping it up into thin rectangles. So from an intuitive standpoint, this seems like a good idea. And look, this is very, this kind of stuff happens in your day-to-day life. You don't really even think about it. Everyone here is familiar with video. I mean, we're watching me on video. You're familiar with watching movies. Does anybody know what a movie was called originally? It wasn't called a movie. The original name of movies were called moving pictures, because that's how recordings work. You're essentially taking a bunch of images and moving them so fast that it confuses the mind into thinking something's moving. A very similar thing is happening here. We keep taking more and more rectangles. And so as we increase the number of rectangles, their widths must keep getting smaller and smaller, because I'm not making the widths bigger, they're shrinking. So what's happening is that the width of these rectangles relative to our eyesight is shrinking to zero. So as the number is going off larger and larger and larger, the widths are shrinking, shrinking, shrinking. And that's why these 500 pink rectangles really just look like the region under a parabola. Does anybody have a question or a comment? All right, so now we need to go back and do the math behind this. So the idea is to approximate the region with rectangles and recognize a pattern. So let's do this by hand, and we'll start with a small number of rectangles so we can see the pattern, and then we can investigate the pattern. So if I go back to this page, let's start with 4 rectangles. So how can I do that? Well, let's do it as simple as possible. I'll break it into 4 pieces. This is 1/4. This is 1/2, but it's going to be useful for us to think of this as not as 1/2, but think of it as 2/4. And then, of course, we can think of this as 3/4. And it's also useful to think of 1 as 4 over 4. And so let's draw these rectangles. Here's one. Here's another. Here's another. And here's another. And the nice thing about these rectangles is the heights are very easy to determine, as are the widths. So if we go to the next page, we can easily write down this sort of sum. So the area of the 4 rectangles is, well, let's denote it with this A with a subscript 4. So what is it? Well, the first one has width 1/4. What's its height? Well, its height is 1/4 squared. The next one has width 1/4. Its height is 2/4 squared. The next one has width 1/4. Its height is 3/4 squared. And then last but not least, the last one has width 1/4, and its height is 4 over 4 quantity squared. So why am I squaring all those terms? Well, remember, each one of those points is on the parabola, so the height, the y-coordinate, is input squared. Now, of course, we could do some sort of cleaning this up. Everyone has a 1/4, so I can pull that out. And in fact, everybody has a 4 squared downstairs, so I can essentially write this like this. Look at that pattern. So more succinctly, this is 1 over 4 cubed. And then it's 1 squared plus 2 squared plus 3 squared plus 4 squared. Does anybody have a question about this? Now, I could go to a calculator and add this up, but what's important is not that we want to add it up right now. We want to recognize a pattern. So let's put a star next to this for now. And then, of course, we can add it up if we'd like. So if you go to a calculator and do this, what you're going to get is the following. Well, I hit the wrong button. So I got the wrong answer. That's never good. So if you go to a calculator or you do it by hand, I mean, you could use a calculator. What you end up getting is this becomes 15 over 32, which is approximately, well, I shouldn't say approximately. You can actually compute this one. Get the exact decimal. 0.4686. 0.75. Does anybody have a question? Now, here's what's cool. Here's what one of the one of the things that mathematics is really all about. It's about recognizing patterns to make computation simpler, and it's about seeing things from different perspectives and realizing it's just the same thing. So if instead of using 4 rectangles here, if I wanted to use 8, we can do the following, and I highly encourage that you do this on your own. So if you use 8 rectangles, like we did before, what do you get? Well, we'll denote that number a sub 8. What is it? Well, the width is going to be not 1/4 anymore, it's 1/8. And then the first guy's height is going to be 1/8 squared. And then the next guy has width 1/8. And then it's 2/8 squared. And this pattern continues all the way out to 1/8 times 7/8 squared. Plus the last guy will be 1/8 times 8/8 quantity squared. And just like we did before, this simplifies to 1/8 cubed times 1 squared plus 2 squared. You should check this for yourself. Plus 3 squared, all the way out to 7 squared plus 8 squared. Again, I highly encourage that you do this on your own. Does anybody have a question? What do you mean another 1/8? That's 1/8 cubed because everybody downstairs has an 8. So there's an 8 squared and 8 squared downstairs everywhere, and everyone has a 1/8. So it's really, everybody is a number squared over 8 cubed. So you can just pull the 8 cubed out. Does that make sense? No, no, if you go back, it's 1/4 times 1/4 squared, which is 1/4 cubed. So make sure, yeah, this is, again, the pattern's identical. That's a good question, though. Okay, so if you do this correctly and you go and do the arithmetic, you can show that this is 51/128, and this simplifies to approximately 0.39843. Okay, so here's where recognizing patterns is great. You could do this all you want, but why do it for specific numbers? Why not be a little more creative? So for n rectangles, and n can be any positive integer, for n rectangles, you have 1 over n times 1 over n quantity squared plus 1 over. Now I know this gets a little more frightening when we have these letters sticking out here, but this pattern also works for a general n. And so just like we did before, we get this. Now, what number comes before n? Well, that's n minus 1. So you have to be a little more careful how you write this out. But the pattern is the same. And so what happens now as n goes to infinity? Well, let's do a little experiment. Let's experiment. Now, I'm going to be doing this using computer, but this is not hard to do. I would be happy to show you how to do it, but I don't want to go through all this by hand because it just takes too long. So let's investigate. So how am I going to investigate? Well, what I'm going to do is I'm going to make a table. So what I'm going to do here is in this column, I'm going to tell you what n is. And then in this column, we're going to tell you what the area of those n rectangles are. So we already did the first two. So let's write this in a color that's going to really appeal to us. So let's say when n is 4, we already calculated that we got 0.46875. So then then we did 8, and when you get 8, what did we get? We got the 0.39, right? So it's 0.39843. So let's just, for fun, let's go up to 20. And again, you could write this out and do it all by hand, but using a calculator, we get that that's 35875. Double that to 40. You get 0.34593. So now, since we have calculators helping us, let's just do it to 100. And when I do it to 100, I start to notice that there's a pattern happening here. So I say, what if I do 500? When I do 500, I get 0.334. 334. And so now I say, let's go to 1,000. When I do 1,000 rectangles, I get 0.3338. And so if I say, okay, I'm starting to recognize what's happened. What if I did 10,000 rectangles? I do 10,000, I get 0.33338. And so if we continue like this, we have some sort of pattern, another pattern formulating. So what does it look like? It looks like as n goes to infinity, a sub n is going to 1/3. So notice I said it looks like. So the question then becomes, can I verify this? Logically. Does anybody have a question or a comment? All right, so how can we do this? It turns out we're going to need some sort of ingenuity. Actually, I shouldn't say ingenuity, because that makes it seem like only the brightest would ever make sense of this. Some help from patterns. So it turns out the following is true. And some of you may have seen this in an algebra course or something, or another course. It's a very useful fact. And we're going to state two very important facts. The first thing is, for any positive integer n, well, I guess this is for both, so let me fix this. So for any positive integer n, the first thing we have is we have that 1 plus 2 plus 3 all the way up to n is always equal to n times the previous number all over 2. And we also have a very similar pattern if we want to sum the squares. So these two identities can be derived in a few different ways. I'm not going to do it, and maybe some of you have seen it before. The first one is pretty straightforward. The second one is not so straightforward, but you can verify these things. And the importance of these things is they allow us to rapidly do. So if you noticed how I was getting these numbers, you might say, how was O'Grady getting these numbers so quickly? How I was getting these numbers so quickly is I was using these formulas. You can verify that they're correct for the first few values. I mean, let n be 3. What do you get? For the first one, you get 6 over 2, which is 3. And guess what? 1 plus 2 plus 3 is equal to 3. So in our numerical investigation, numerically, if we did a bunch of computations, the computer keeps telling us this looks like as n keeps getting bigger, that the area of the rectangles keeps getting closer to this 1/3. And so what we can do is we can use these formulas now to logically verify this. So thus, a sub n, which we said before was 1 over n cubed times 1 squared plus 2 squared all the way out to n squared. This is 1 over n cubed times n plus 1 times 2n plus 1 all over 6. And now it's just some algebra that we can do. Some of these n's cancel, so I'll get my red marker. This cancels with one of these. So you're left with n plus 1 times 2n plus 1 over 6n. And of course, if you multiply this out, this is 2n squared plus 3n plus 1 over 6n. And now what you need to recognize is as n goes to infinity, this goes to 2/6, which of course is 1/3. Does anybody have a question about that? So you might say, where are you getting the 2/6 from? Well, this goes back to when we were talking about limits at infinity in horizontal asymptotes, if you remember doing that. And some of you may even remember this from like a pre-calculus course. Okay, so what does this sort of suggest? So the previous example suggests we might define area in a similar way. So what do I mean by a similar way? So this is gonna maybe be a little scary. given a function y equals f of x, that is positive on some interval. Now, I'm not going to use 0, 1. I'll use a comma b, some generic interval. We can create a region bounded above by the curve and below by the x-axis. So let's just draw that picture in a second. So again, we have a curve. The reason we say it's positive, that means the graph is above the x-axis. So let's draw what this might look like. So here's an example of what it could possibly look like. Call this guy A, maybe B's over here, and the curve has to be above the x-axis on AB, so maybe it looks something like this. And so what we're going to say is this region right here between A and B and the x-axis so the area of the pink region is the limit as n goes to infinity of a sub n, where what is these a sub n's? Well, we have to, you know, this might take a little bit of sort of filling out the details on your own, but what is a sub n? Well, a sub n would be 1 over, what is the width of the interval going to be? So this is pretty challenging, so you got to be sort of bear with me. I'm going to use this symbol delta x. So this is going to look very frightening at first. What is delta x? Well, that's the width of each interval. So that's the total width of the interval, b minus a divided by n. And what are these x sub 1s? Well, x sub 1 is equal to a plus delta x. X sub 2 is equal to a plus 2 times delta x. In general, x sub n is a plus n times delta x. Scary. Lots and lots of scary symbols. Lots happening. Does anybody have a question about this? So again, what does this represent? Well, if you want to think about it, all these f's, the function evaluated at a point, those are the height of each rectangle. And the width of each rectangle is delta x. Hold on a second. Pardon me. This is incorrect. I wrote this wrong. This is not 1 over delta x. Ooh, fix that immediately. It's delta x. This is the width of each rectangle. Okay, so you said you're confused how I got x sub 1. Well, okay, so x sub 1 is the first point. So it's got to be a distance of what? It has to be a distance of the width from A. So the best way to think about these x sub 1s, x sub 2s, x sub 3s is to simplify it and think of A and B as 0, 1. So, okay, so perhaps here's a good way. So, okay, so does it make sense? Yeah, again, this is not, look, this is hard to learn. You're going to have to, if you want to learn this, it's going to take a lot of time on your part, and you're going to say, we don't have that much time. I know, we're learning this in the summer, and we're rushing around, but draw a number line. So pick numbers for A and B, Emily, and it could be 0, 1, or any two numbers you want, and then draw a number line, and then practice saying, I'm going to do it in the 4 pieces or 8 pieces. And then you'll see where these patterns come from. So, yeah, and I'll be honest, guys, you know, for me, when I had to learn this, look, it's overwhelming. You're sitting in a class and some knucklehead like myself or some professor is throwing all these subscripts and numbers everywhere. And look, it's going to get even more crazy because we're going to do new notation in a second. The best piece of advice I can give you is to draw pictures on your own and go to the internet and watch videos. Maybe, I mean, obviously you want to look at what we're doing, but it's challenging to learn. So, you know, every time you think you might have figured it out, you're gonna come back to it an hour later and be like, what the hell? You're lost again. Okay. So, and by the way, as some of you already know, this way of computing area is, we're going to find out it's a lot easier than all this, but we have to get to that. It's okay. So let's put this down. So the bad news, the previous page is scary, whatever that means. The good news, we will find a different way, or find an easier way. So more good news is the sum on the previous page. Let's not just say on the previous page. Let's just tell you what it is. So this sum, this delta x times f of x of 1 plus f evaluated at x of 2. It has a name. It's called a Riemann sum. And it is used for many applications, not just area. So the analogy here is way back in the beginning of the term when we were studying the derivative, we motivated the derivative by asking this question about tangents. And then what I told you is the derivative is way more useful than just tangents, and hopefully you figured that out the last couple weeks. And so instead of just calling it the tangent, the derivative is called the derivative because it can be used for a whole lot of things. And so this type of sum right here turns out to be extremely, extremely useful for all sorts of applications. So one of the applications is area. It's not the only one. And many of you will find out next semester and beyond in other courses how useful this sum is. And because of that, we give it a name. So if f is continuous on AB, this limit, the limit as n goes to infinity of delta x times this guy exists. So we give it a name. We call it the definite or Riemann integral of f on A comma B, and we denote it by this symbol. So now we're introducing some new symbols. It's an elongated S, and you put A here, and you put B up here, and then you put f of x, and then you put a dx here, and it is equal to this limit. Ooh, that's scary. There's a lot happening here. So let's look at this notation a little more, just because you need to have some terminology. Whoa. We write this like this. Let's give some names to these things. This is called the lower limit of integration. Or the integral. This is called the upper limit. The function that we are integrating is called the integrand. And you can think of the dx at the end as sort of like a grouping symbol for now. I mean, it's a little more than that, but it's essentially telling us what the variable is. Does anybody have a question or a comment? All right, so we're going to give some problems to work on these, and then hopefully you'll ask questions. And then on Thursday, we'll learn the shortcut, which is nice. But the shortcut is only a shortcut when things are behaving a certain way. So you need to keep that in mind, and hopefully we'll wrap it up. Does anybody have any questions or comments? So please, you know, try to work on the next assignment before Thursday so you can ask questions, because you're going to need to know some of this stuff. I mean, not if not all of it, for the exam. And I understand that it seems like we're rushed, but that's just the nature of a summer course. We take finals the last, sort of right when the class ends. That's just how it works. So we're going to make the best of it, though. Does anybody else have a question, comment, concerns? All right, well, listen, please reach out if you have any questions or comments. We want you guys to do well. Please submit any work you're missing, even if it's late. I don't care. Submit it. Better late than never. And I thank you guys for joining in, and I hope you learned something. So this stuff is hard, so good luck, and reach out if you have any questions. I will talk to you soon. Take care.